Cool.
Yep, I am recording now.
Oh, awesome. So yeah, as Seth said, I'm Makinde. I'm going to tell you guys a little bit about entanglement measures. Um, so there are a ton of different ways to talk about entanglement, and basically every different division in physics has their own way of like grappling with it. So I'm going to give you like a super rushed kind of crash course or introduction. And as the talk goes, I'm going to hone in a little bit more on things that tend to be more interesting for condensed matter theorists, and also people who are a little more interested in equilibrium phenomenon, specifically stuff that kind of relates to what we've heard before. Um, so yeah, um, break this up into about 3 parts. I'm going to give some general background so you kind of understand what entanglement is and how we think about quantifying it. I'm going to talk specifically about entanglement entropy, which is one measure, and give a motivating example to show how difficult it is and try to provide intuition. And then because that might take a little while, by the end, hopefully we'll have built up enough intuition so that you can understand the different measures and why they're interesting almost entirely on intuition. So that's the hope. So yeah, now if we want to talk about entanglement, basically we care about entanglement because you can talk about quantum mechanics primarily as a theory of correlations, because measurements don't always have determinate outcomes. The best you can really do is talk about correlations between one measurement, or one operator, and another. So entanglement is kind of uh, the residual correlations that are fundamentally or irreducibly quantum. Again, most people have a really good idea or some familiarity with an entangled like system, what it looks like, but quantifying it can be kind of confusing. Um, so as an example, the most familiar entangled state is like one of these Bell states. You have 2 spins up correlated with 2 spins down or in a superposition. And whatever basis you look at these things in, it's always entangled. You cannot separate them. In contrast to that, you have a pure product state where you have, say, one spin in a definite state, and another one, say, in a superposition, but you can split them up very easily. You could get a slightly entangled state by adding another one onto this product state, but that one, the degree to which it looks entangled will look different in different bases. So it helps to try to put a little more structure into this understanding than just looking at superpositions. So what do you need? Well, you need a decomposition scheme. You need to talk about this qubit versus another, or this system versus another. You need to identify which states are special, which ones are not separable. And then you need the explicit quantifying metric which distinguishes them. Oh, my bad. So there are kind of 2 ways to do this. Because it's really easy, or it's, we have a handle on how to do this for 2-state systems. With 2 qubits, you can figure it out. At worst, it's a 4x4 matrix. But for many body states, which is where I'll be putting most of the attention in this talk, it's actually a much more complicated affair. Because we have intuition in the 2-state system, handling many body states kind of comes from different intuitions from that handling. If you're interested in equilibrium systems, or if you're interested in looking at ground state wave functions, the one that comes most naturally is like a bipartite or small number decomposition of some system. Example is just take some spin chain, look at some number of spins together, say L, and then the rest of the system is the other subsystem. So then you have the intuition of entanglement between one section and another. It keeps that nice simple intuition of there's a linkage between these things. Entanglement quantifies the correlation between these 2. The other side is you can talk about, well, we understand entangling between 2 states. well, why don't we talk about entangling two states and entangling another two states, and then through that, building up a different state, building up a final, much more complicated, much like multi-particle entangled state. So this you can achieve by acting with a bunch of unitary operators that act on two states. So there are two different ways of kind of looking at a very complicated, complicated affair.
Can I ask a question?
Yeah, for sure.
Let's see if I can phrase this correctly. So, as you pointed out, entanglement entropy in a region or whatever is completely determined by the correlation functions of operators.
Yeah.
In that region, right? But normally, if we're computing correlation functions of operators in some system, normally like some many-body system, normally what we would do is we would compute them. We would like quick rotate to imaginary time and compute everything in like a statistical mechanics model, right?
Mm-hmm.
Like you can always map correlation functions in some quantum mechanics model to other maybe complicated correlation functions in a classical one, right? So when you say that entanglement is like intrinsically is like the intrinsically quantum part of correlation functions, what exactly does that mean if I can always compute correlation functions in a stat mech model? It's classical. Does that make sense?
Yeah. So I think what I'm gonna say is my intuition. I'm not gonna say this with entire certainty, but I think the best way to talk about this, and Lord, I do not know how to get this thing on full screen. The difference is if you look at a system, like you can decompose different systems, you can kind of always make a quantum system look like a statistical system. You keep on reducing your density matrices down to smaller and smaller subsystems. So you can kind of always look at a quantum system as though it is some kind of stat mech model. Just by Wick rotating it, I'll be completely honest.
I guess like Mockingjay and I are both taking quantum computation at the moment. And like, when I think in quantum computation, like you refer to something as intrinsically quantum mechanical, that's just the idea of introducing like entanglement or correlation, which isn't there classically, like in a computational model. But I guess when I was thinking intrinsically quantum mechanical, I wouldn't necessarily think like you can't get this in a statistical physics model, but just like maybe specifically in computation. I don't know, that like when people say intrinsically quantum mechanical, it always tends to be like quantum computation.
But what is that?
So there's one way that I can talk about this a little more, why I was talking about density matrices in like 2 slides. Also, I need to figure out how the hell to does anyone know how to pull up full screen from just the TechAid PDF? So I think there was something corrupted with
Does the little green expand at the top work?
It does this, if you can see.
Okay.
Subpar, but I will do it if that's the best we have.
Let's see, maybe increase your scale at the top.
No. Nope.
Okay. Yeah, I don't know then.
All right. Well,
I'm just gonna just open it in preview, right? Can you just open it in preview?
Yeah. Give me a sec. Where did I put this ish?
Yeah, basically what I'm saying is that you know the density matrix on a subsystem is you can show that a density matrix on a subsystem is completely characterized by the correlation function of operators in that region. And to me, I don't understand if you just hand me like a set of correlation functions of some operators or something, I don't understand how I could tell you that, oh, these correlation functions come from some quantum system rather than some classical system, right?
So yeah. Let me punt that for like 2 or 3 slides, and then I'll give a partial answer. And then I suspect it won't be fully satisfactory. So let me say that I'll try to bluster through it a little more at the end. Is that cool? Yeah, but if we have the two different distinction schemes of like decomposing something into 2 different parts and having actions on like 2 state systems, those can be useful for 2 different perspectives or kind of agendas. One is if you want to characterize quantum phases, if you're looking at some kind of ground state, then you might want to look at the different types of entanglement, particularly between different bonds in that state. So the one I have pulled up here is from AKLT phase, where you have different bonds, where you can literally see that one of them is the singlet state, which should be maximally entangled, at least from our intuition. And the other one looks like it's similarly, but not necessarily the exact same. So for certain ground states, you ostensibly should be able to distinguish what phase they're in based on whether or not adjacent states have some kind of special bond or like they're highly entangled. And below this, I forget what phase I pulled this from. I think it was just like a random spin coupling. But again, if you provide a specific cut, you should be able to kind of quantify or think about the number of states that are entangled across a boundary. So again, kind of splitting up to count the amount of entanglement going across something between the 2 systems. And in this other perspective, because you have unitaries acting on things that are slowly entangling adjacent systems, that's useful if you want to look at entanglement dynamics or entanglement spreading. That's very useful for non-equilibrium systems. I'm not going to focus on that just because I'm less, I know much less about it. And I think it's a little more difficult to explain in a short period of time. So we're going to focus on the characterization or decomposition schemes. So this is where I think I can start addressing your question a little bit, Ethan, which is if we want to talk about entanglement, if we want to give some kind of measure on it, quantify the amount of information shared in these correlations, well, then we want to have some kind of probability distribution. We want to have something by which we can quantify all of this. So this is going to look a bit different if we talk about a pure state, if we talk about a state that we know is just one in a Hilbert space that we know very well, we know the entire system, then all we have to do is think about the different projection operators or the different like subspaces that our operator will decompose the system into. Alternatively, we could think about being in a mixed state. Say we only know about a system, but it is coupled to something else, in which case we can really only talk in terms of mixed states. So yeah, we have this whole jumble of things, but the probability isn't just coming from the wave functions we have or the wave function we're given. It's also coming from some kind of coupling to something else. So long story short, we can talk a little bit more about this, Ethan, but my intuition or my concern is that something in the Wick rotation procedure might make it so that you're not necessarily maintaining the pure state structure. I'm not gonna say that I fully back this, but it would make me more comfortable that it becomes a pure stat mech model. Anyway, I'm gonna move on because I'm probably blowing hot air. But now if we want to actually talk about information, well, an easy place to start is classical information theory. So what I have on the left is the classical Shannon entropy, which if it's a uniform distribution gives you your usual KB log n formula for entropy. So we can literally just translate that into a quantum formula. So we can now talk about the entropy in terms of a density matrix, because we can get probability distributions from this density matrix. So instead of talking about a sum over probabilities, we're going to trace over a system defined by the density matrix times the logarithm of its eigenvalues. This has some nice properties. If you act on the density matrix with any kind of unitaries, it's not going to change the entanglement entropy, which you would hope, since unitarity shouldn't allow that. It's positive definite, and it's only 0 when it's pure. So that's going to be very important. So if you have a pure state, the information is basically telling you that it's not, there's nothing with which it's entangled. It's just that state. When we decompose things, that's going to be a little bit different, because now we're going to be talking about the density matrix for that subsystem. Also, it's bounded by log d, where d is the dimensionality of the Hilbert space in which it lives. And it only saturates when it's maximally mixed. Basically, when something is just a bunch of bell pairs across a system, each bell pair will contribute, as we'll see soon, will contribute like 1 bit of information effectively. The last bit is effectively something that has to do with observation. It's like a convex operation, which basically means that if you measure a state and then you become certain that it actually is something, you have a distribution of all measurable states, then your entropy is actually going to go down. You can learn by observing. That's basically what the last condition is. So now, if we want to look at this in terms of a spin chain, we can kind of break this down for, again, this simple 2x2 system. If I take this Bell state and now I write down its density matrix, it's a really, really simple 4x4. I can just take a partial trace. It gives me the simplest 2x2 ever. And then I can just compute it by hand extremely easily. So I can get the entanglement entropy is just log 2. And what that number actually tells me is basically the number of states that are entangled across this border. So in this case, I just have 2 spins sitting next to one another, and I cut a line in between them. And what the entropy, the entanglement entropy here counts, is the number of states that are entangled across this border. So if I were to do this with k states, I just put a system of everything coupled up and everything coupled down, or a bunch of copies. Well, then I just get k log 2. So again, it's roughly just a number of counting across. But also, if I were to take one of those states across the boundary and move it across, then I could construct a pure state with that number of qubits. So you can either think about it as the number crossing the system, or the number that you need to put into a subsystem if you're just thinking about it on its own to purify it, to make it into a pure state. Again, if anyone has any questions, I'll answer them. I may punt them to the end. So on that last point, the purification operation can kind of always be done, or at least in principle, because if you have some kind of bipartite system, even if it's in a mixed state, you can always find a basis with which to diagonalize one side. I'm not going to spend too much time on this, but basically, you can always find a way to write your system. If you're only thinking about your density matrix in A, you can always construct something that will purify it by adding on another Hilbert space of at least that dimensionality. Yeah. So now I'm going to focus on entanglement entropy, what we just saw before for the two-state system. And I'm going to talk about some 1D spin chain models that'll hopefully give you a little more intuition. So first of all, if we take just an arbitrary 1D model, consider some small region of L spins, and then think of the most generic state possible in this space. So we haven't put any constraints on it whatsoever. But now we consider this region to be small relative to the size of the entire system. Well, if you consider the amplitude for each of the spin states to be just arbitrarily drawn, so as random as possible, then for basically any system that you choose, it'll be maximally entangled with B. You can kind of think of this as it being entangled as kind of a random choice, but there are so many choices outside the system. So it's effectively going to be entangled as much as possible with the rest of it. So the entanglement that you would expect is going to be proportional to the volume or the size of A. That's not the case for specifically ground states, but other phases that we're going to see later. So let's look at some concrete models. We'll do the same thing. We're going to look at a small region A with L spins, and we'll take the other section, the other part of this decomposition, to just be the rest of the system. So a generic state is just going to be some excitations above the ground state. That will be important in just a second. But for concreteness, we're going to look at the XY model, and we're going to look at the transverse field Ising model. So these are super simple 1D spin models. And we're going to see how to get the entanglement entropy and what its properties look like. The easiest way to do this, since we're going to be looking at the ground state as a unique one, which shows some interesting properties, well, we need to actually have an explicit way to write the ground state. In the formulation and spin operators, it's a little annoying to do it in some kind of continuous way. So instead, we're going to take a Jordan-Wigner transformation, and we're going to look at this thing as in terms of fermionic operators. So for the XY model, it's real simple. We just get some kind of very easy whatever. We get some simple simple model here, which has some kind of cosine dependence. For the transverse field Ising model, if you're familiar with it, you can do the same thing, but the operators you get are Majorana operators. This will be important because of the excitations above the ground state in a little bit. But the most important thing, so we'll focus on this XY model, is you get different regimes. So you can talk about the regimes where this effective magnetic field, this lambda parameter, is greater than or less than the absolute value. It's greater than or less than, it's outside 2, in which case either all of the fermionic modes are occupied or they're unoccupied. If you look back at the model, this is effectively when everything is aligned with this magnetic field. But if you go within that boundary, the absolute value of lambda is less than 2, then some of these fermionic modes are occupied and some aren't. So you're no longer, in the spin language, you're no longer locked onto the magnetic field. What that means here is that, well, some of the modes aren't occupied, and you can explicitly see that, that some below some particular K threshold are going to be unoccupied. So now we want to link this to explicitly the density matrix, but to do so, we're going to go kind of roundabout, and we're going to link it to a specific correlation. So thankfully, that's really, really easy in this case, because all of those below a certain threshold are going to be unoccupied, and those above it are going to be occupied. So you have a stupidly easy expression in terms of these momentum creation and annihilation operators. And you can translate that into position space, which we want to do since we're limiting to a local region, fairly easily. So you can explicitly show that you get this sum of cosines up to some critical k threshold. And the thermodynamic limit, you can literally just do this integral and you get some sinh function. So now the whole trick, which isn't hugely important, but it is shown kind of for the miracle that it is that we can solve this exactly, is that you can simultaneously diagonalize this really nice correlation matrix and the density operator by just doing some nice unitary transformation to show that the correlation matrix is diagonal if you restrict to this region of L spins. And the fact that they're both simultaneously diagonalizable means that our density matrix is also diagonalizable and in this nice basis. So we can effectively split it into a bunch of decomposed subsystems, one per qubit. So because of that, and because we know how to calculate the entanglement entropy for a single qubit system, we can calculate it for the whole chain as just the sum of this entanglement entropy for each subsystem. So you get L terms, each of which should just look like the entanglement for the 2x2 matrix describing that spin, which is given with the eigenvalues by this H2 operator. Details of this aren't hugely important. You'll let me know if you want to know a little bit more. But basically, it's kind of a miracle that you can get an exact form in this case. And if you do this, you can sum up all of these different parts. And from it, you see in the phase where lambda is, the absolute value of lambda is less than 2. So in this, in that phase, the XY model actually shows logarithmic scaling with the length of the system. So what that means is if you have a really, really long system, effectively the number of particles outside the system with which you're correlated isn't going to scale with the volume or the length as it did before. It's going to have some kind of sub volume scaling. In contrast, you can do the exact same procedure for the transverse field Ising model, but that logarithmic scaling only shows up exactly at this critical point, exactly at this transition between the two different phases. If you're outside that phase, what actually happens is that the scaling eventually saturates to a constant. So that hopefully should make a little bit of sense, because outside that particular scaling, you should either be in the phase where all the spins are aligned or where it's effectively random. And in that case, well, the bonds across either that you're correlated or that that you're not. And they should only really affect the states on the boundary. You can kind of reason that through, regardless of how big your system is, you're either correlated or you're not. So yeah, it kind of makes sense that it would go to a constant. That's not the case for the XY model in this particular region, for the transverse field Ising model at this specific critical point. That has something to do with some of its scaling properties. Both of these can be cast in the language of CFT, where you can actually explicitly show that the scaling should depend on the central charges of this CFT. And those central charges will be different whether you have fermionic degrees of freedom or bosonic degrees of freedom. Um, so this is interesting because looking at this scaling at the critical point, you can actually distinguish whether or not the fundamental degrees of freedom, the excitations about the ground point, the ground state, are fermionic or bosonic. So remember, we started with an arbitrary spin model. So we didn't, I mean, they look kind of the same, but because of what's going on at this critical point, you can actually distinguish. In one case, we cast that it had Majorana operators, that they were fundamentally in some sense fermionic, whereas in the other case, the operators still seem to be bosonic, even though we found this by using fermionic operators. Happy to talk about that a little bit later, but that's one of the reasons that the scaling relations in entanglement entropy can be very useful. Sometimes you can distinguish what the fundamental degrees of freedom at play are. So that was one of the cool things that you can get out of it is these scaling relations distinguishing different parts. But typically in an arbitrary ground state, you expect correlations to be kind of local, to fall off with some kind of exponential, with some length scale. And because of that, you expect the correlations will only really affect like a finite number of states outside the boundary or on either side of a boundary. And so typically what you expect is actually some kind of area law in terms of the entanglement entropy. You expect the number of states that are entangled to be proportional to, well, the surface area of whatever subsystem you're taking, because there should be a finite number of either sides of it. But that's not always the case, as we said before. So when that's not the case, you can think about it by, again, looking back at the correlation lengths. So when correlation lengths diverge, well, you wouldn't expect for this area law to hold anymore. If it transitions to, say, a power law, then again, you don't necessarily have that nice finite length scale that you can just count on either side of the boundary. Or if you have another length scale present, say you have a Fermi surface, that can also complicate things, because then again, the counting on either side is a little bit more subtle. So in these cases, typically what you see is some kind of scaling between that which you would see for completely random states, some volume law scaling, and that which you would expect for ground states, this area law scaling. So as an example, it's expected for most fermionic systems that they have a logarithmic correction to this area law.
Can I ask a quick question? It's kind of silly, but
yeah.
So I'm trying to understand the log in one dimension, right? So in the XY model that you're talking about, right? The state that I'm interested in the entropy of is just a bunch of plane waves, right? Yeah.
So not quite, actually, because you're not talking about the plane waves as your fundamental states. Again, you're actually thinking about states living in this restricted subspace. So only the states living in A.
Yeah. So
Right.
like I have the whole chain, right? And the ground state for the whole chain is adding a bunch of plane waves, right? And then I'm interested in the entanglement entropy of a subregion, right?
Mm-hmm.
And then maybe I would have thought it would be like the entropy would be like scale with the size of the region, because like you have plane waves of very low momentum and they go across the whole region, and like correlate the region with its complement, sort of, if you have like really long momentum things that you're stacking up. Is that like
So there's a little bit of a balance, because the low momentum modes, you're right, are going to correlate with the rest of the system, but they're kind of going to do so in a sense kind of like uniformly. So they're not like maximally entangling two specific states. but also you only have a certain number of those states which are going to be like fully counted. So when you talk about the plane waves, you can stack all of them for their full ground state, but when you restrict to the Hilbert space of this restricted region, you only have like L states to consider. So you can only count like so many states in total. So even if you want to take a ton of low energy modes, you can only really like effectively think of like L of them. And because they don't explicitly correlate like one particle in the region with one particle outside, like maximally, it's not going to give you the same like, volume law scaling. Does that help a little?
Yeah. So is there some intuition for why it's log then? Or I guess it's you just told me that it's less than linear for this reason. And then
Yeah,
it's gotta
basically
be log.
the log is, it's not linear and it's not constant, but it should have some scaling. So
Mhm.
yeah.
Cool. Okay, thanks.
Yeah. So yeah, hopefully we've built up enough intuition that you can kind of get a feel that there's entanglement in this framework is really kind of like sharing bonds across a particular barrier. That's really cool, but you lose a lot of detail, and there are some subtleties when you only rely on entanglement entropy, this metric we defined earlier, rho log rho. So one of the big troubles with it is actually not even all the details that you can lose, but actually just that it's really, really hard to calculate or explicitly measure. That's because it's not linear in rho. Also, calculating logarithms of operators is freaking hard. So in practice, basically no one does this. We have a few examples, one of which we went through. But typically what's actually done is people calculate these things called Rényi entropy. If you read some paper on entanglement entropy, you will almost always see this. So these are a bunch of different, effectively like moments of entanglement entropy, which you don't take the trace on the outside, you take it on the inside. And there's this really lovely relationship where if you take the limit as n goes to 1, it will reproduce the entanglement entropy. Intuitively, these things kind of focus a little bit more on the most probable states or modes, because you're taking them to nth powers. If you can calculate all of the different Rényi entropies, that will give you something called the entanglement spectrum. Basically, I just wanted to mention this because if you see people actually calculating this, they'll almost always go through Rényi entropy, even if they're coming back to entanglement entropy. But even if we get through that and calculating it's a little easier, there's still some more serious problems. So before, there may be some interesting details that are not captured with the leading scaling behavior. If we go back to this scaling, notice that in the XY phase, there's a subleading term which depends on the magnetic field. And there's even some kind of constant term for the transverse field Ising model when it's critical. That might contain some information, but because we only care about scaling and it might be really hard to calculate, it doesn't really show up as much in the entanglement entropy. The other issue, which is a little tougher to see, is that it conflates classical and quantum correlations. So again, as we said before, you can have a pure state and you can break it up into two. And when you take the partial trace, that'll give you some kind of, well, your reduced density matrix will now look mixed. It's going to have probability distribution over a bunch of different pure states. But you could just as easily have been given something that had a similar distribution. You could be given something which has probability distribution over a bunch of different states. And so the correlations that you pick up, the probabilities you explicitly compute, those could come from something being explicitly like thermal or coming from classical correlations, or it could come up from your decomposition scheme. But if you want to drill down to it being fundamentally entanglement that's giving you these counts, then you really want to be able to distinguish the two. This can basically be boiled down to a separability problem, that if you talk about entanglement entropy, if you're given the state which is already mixed, it's not always going to be zero. In fact, in most cases, it won't be. So it can't distinguish between, say, a mixed state or one in which you've just chosen a certain decomposition scheme that does have entanglement. So to get around that, there are a couple of formal conditions for different entanglement metrics or measures, many of which are taken as more important than others, and for most measures, one or two of these things is not completely fulfilled. But these are some of the conditions that you would want out of a measure of entanglement on some density matrix. The first is one that we talked about before. If you have a state that's maximally entangled, so you have like a bunch of Bell states across some boundary, then you want your measure to count that. You want to count as much entanglement as possible, where that's the dimension of the Hilbert space. If your state is separable, you can write it as a product state between the two subsystems. Well, you want there to be no entanglement. That's kind of how we define or think about it. This other one is very important for quantum information people. Basically, if you apply local operations, if you transform things on one side versus another, you only want that to be able to reduce entanglement. You don't want to be able to apply local operations and effectively produce entanglement. That's kind of not what it is. And then if your state is pure, you want your measure to reduce to the entanglement entropy. Again, entanglement entropy really has this problem effectively when states are mixed that it can't distinguish. So if it's pure, then why break what works? The other one is convexity, which is similar to what we had before. Effectively, if you're performing measurements or you become aware of a particular state, you want that to give you information, not take it away. There's some more technical things, some notions of continuity, subadditivity, and such, but those aren't really as important for this talk. So here are a couple of flavors of the different measures to show what's really useful, what's intuitive, and what can be really difficult. So one of the first things you might think of if you have, say, a spin chain or a very big multipartite system is, well, I want to see if something is, separable. If I can distinguish all the different states, all the different spin states. So why don't I just say, take my wave function, take the product with a separable state, a state that's separable between all the different subsystems, and then we'll just take whatever the greatest overlap is. So if the overlap is 1, then it's in the class of separable states, and I should have no entanglement entropy. Great. I mean, intuitively, that makes a ton of sense, but it should come as no surprise that it's the most intractable thing to use ever, whether computationally or theoretically. It's effectively just there to teach people about intuition. So yeah, most people don't think about this at all. Alternatively, you can kind of think about this from the idea of creating quantum states. So instead, you can say, well, I want to make a pure state out of this thing. And so I'm going to take an ensemble of pure states, these pi or pj with these pure states defined by the psi j, and I'm going to look for the minimum, the ensemble which minimizes entanglement entropy on these pure states. So what that says is I'm going to take a pure state, I'm going to divide it in the same way that I have my full subsystem, and then I'm going to see what ensemble of pure states, which reproduces my density matrix, minimizes this metric. This kind of tells you the amount of bits you would need to add to a system to take it to one of those pure states, the like expected number to like get a pure state out of it. In some formal limit, you can actually show that this is equal in like a thermodynamic limit to literally the number of bits you need to add to create a state, create your state out of one which is completely separable. Anyway, this is one again, which is of a different motivation of kind of creating something, but because it's this complex minimization over different ensembles, again, it's really, really computationally demanding, theoretically challenging to do, and I think it's only really been accomplished for 2-qubit systems. So again, it's challenging. One of the more interesting and more useful ones is something that's called conditional mutual information. This one is another minimization if we want a formal metric, but it's based around something which from classical information theory is the conditional mutual information. And what that is it's basically saying the information shared between a subsystem A and a subsystem B, given that you have information or you're conditioning on some additional or third system C. You can literally write this out in terms of the entanglement entropy, or in classical information theory, the information entropy, as this distinction of these different phases. So the entanglement of a subsystem AC, BC, taking out that third bit, and removing the entanglement of the whole system. Basically what this is saying is if I add some additional system C, if I choose some system to put onto my original composed of a bipartite distinction of A and B, how much information is shared between the two, given I'm like purifying, I'm trying to add more to the system. So if you can minimize it and there's still some shared information there, then those states have some kind of very fundamental entanglement. That's the intuition. Again, this one can be slightly difficult because of this minimization procedure, but because it's comprised of just entanglement entropies of well-defined systems, it's a little easier to get a handle on. The last metric I'll talk about is this negativity, which is just a log of the trace norm, a norm of this partial transpose of a system. This operation is what happens if you take your subsystem A and you transpose all of the different states in there. I'll show a little bit later that this operation really hones in on whether or not your system is separable, because this partial transpose operation does not take density matrices to density matrices if the full subsystem is not pure. Sorry, is not separable. I'll show that in just a sec. So again, going back to why we should care. So in 2 dimensions, entropy typically has this this area law scaling, so scaling with the length, but there's also an additional term, a subleading term, that can tell you whether or not you have topological order. So the clearest example, I think, is if you look at, say, a toric code. So you have a bunch of different operators living on the links of things, And basically, you can think of the ground state as all of the closed loops going around links. So it's going to be a huge superposition of a bunch of different states. But now if I want to think about the entanglement that would come out of a particular subregion, well, I can kind of do that specifically by looking at the links that cross this boundary. Again, since there should be closed loops for some ground state, then if I think about all the different states that I could have in this restricted subregion, basically I should have all the states which have just as many links leaving the subregion as are coming in, or there should be an even number of those things. Basically, because if I have a loop that goes out, at some point it either has to go in, or it's internal, or it's external. There's no odd number for the ground state. Because of that, you can literally just count up all the possible states that you would have in this subregion. And that should be something like 2 to the like L minus 1, where L is the length of this boundary. Because of that, I mean, you're literally just talking about casting out all of the odd jumps from one side of the boundary to the other. You would expect an entropy something like L minus 1 log 2, basically giving you some logarithmic, some linear scaling, and then some constant, just this log 2. And so for the toric code, of course, if you transition to a different phase, then you would lose this constraint that all the loops have to be, all the loops going in have to come back. And so that will distinguish the types of phase that you have.
Wait, so should it be alpha L minus gamma in 18?
Sorry?
Or am I, should it be alpha L minus gamma in equation 18, or am I confused about this?
I think you are right.
Because the entropy goes down because you know more stuff, right?
Yeah, I think so. Yeah. You know more stuff, so the gamma is actually, I think the gamma is for the phase when it's put in the topological phase, so you go up by log 2. So if you have a loop going around the full your full toric code, then you're in one of the topological phases, and you go from like negative log over 2 to 0, or however you scale the thing.
But shouldn't your, I mean, the constraint of the number of loops, you know, hitting the boundary being even, shouldn't that like reduce the entropy relative to the?
Yeah, that's you're right. It should be negative.
Okay.
It was just the sign of the gamma is positive when you're in a topological phase. In the topological phase is when you have like a loop going all the way around, so you can have an odd condition.
Oh, I see what you mean. But well, yeah. Okay, but when you look at a region that is but you're looking at like a topologically trivial region or something, right? So
right. So this is topologically trivial. But if you move to the topological phase, basically you're adding on something which could be more. So when it's in a topological phase, you don't have this condition. So your entropy should just be log 2, and you moved up.
Yeah. Okay.
Yeah. Anyway, it's not that big a deal, but you're right. I missed the anyway. Yeah, but the reason you should care is that you can actually capture this topological entanglement entropy using one of the metrics that we defined before. You can calculate it using the conditional mutual information which we defined before. This is a little annoying. This is basically breaking your system up into 3 parts instead of 2. And it's, yeah, you have to break it up kind of cleverly. You can also do it by just taking the entire system in 3 parts, but then you get something slightly more complicated, which isn't exactly equal to the conditional mutual information. But effectively what you get is you look at the correlations between A and B, the information shared between A and B, given that you loop through some extra region C. So it's saying that you have some correlations there, but I'm also allowed to think about traversing something going all the way around. It's nice because it's, again, always greater than or equal to 0. It's a positive definite thing. So you always get some kind of positive topological entanglement entropy or none at all. And one slight subtlety, if you want to actually calculate these things, is you want to make sure that these regions are taken to be very large compared to the correlation length. Otherwise, your counting of different states might be off. Oftentimes, both this system and these regions are taken to infinity. Anyway, again, this is like a counting of different entanglements across different regions, and you're just carefully picking out the decomposition so that you capture where they're coming from. So now I'm going to talk about a little bit about entanglement negativity, which is something I've been working on a little bit more. And this one is much less familiar, it's slightly newer. So this one is just a log of something called a partial transpose. And this is interesting because you can kind of use it either as the typical bipartite decomposition, whereas before with the entanglement entropy, you just talk about, you're considering subsystem A and subsystem B, or you can actually kind of make this act a lot like the previous case where you have a tripartite, a 3-state decomposition. So that's possible because when you do this operation, you take the partial transpose, which I'll explain in just a second, over a particular subregion of a density operator. So as before, you could treat this kind of like the entanglement entropy and have that density operator be that for a particular region. So in the case of example A, I could take the partial transpose over the region of L spins, and that would give me an entanglement negativity for that. In case B, I could do the exact same thing and divide it into 2 sections. Or in the third case, I could take the reduced density matrix for L1 and L2, and then partial transpose over one of those subregions. That's going to be the one I want to talk about the most right now, because that allows for really sensitive detection of entanglement between the 2 regions we're talking about. So as I said before, this partial transpose operation really hones in on the separability of a particular density matrix. And the reason that's true, I'm just kind of going to go over it intuitively, is if you have something that's separable, if you have a density matrix that's separable, you should be able to write it as some kind of sum of, well, decomposable parts. I have density matrix in region A, density matrix in region B. And so if I apply this partial transpose operation, basically that just means take all your density matrices in region A and transpose them. The nice thing, though, is if you have some kind of density matrix, transposing is going to leave the spectrum invariant. You're still going to have some positive definite eigenvalues. So you should that operation should take you from one set of density matrices to another set of density matrices. If the system is entangled, that's not necessarily the case. You're going to be mixing things up in a really, really random way. And ostensibly, there's nothing that says that this needs to remain Hermitian. There's nothing that says that the eigenvalues of the full system are now going to stay positive definite. And so that's effectively what this checks. The operation basically counts the number of the sum of the negative eigenvalues that amount from this. It's like two times the number of eigenvalues plus 1. But basically it counts how far you are from satisfying this criteria in some way. As we said, because this thing, if you take this partial transpose and you go from one density matrix to another, then you're just going to have another density matrix when you apply partial transpose to a separable state. And then, as we did before, you take this trace norm of a pure state, or some, if there are no negative eigenvalues, then I think this might not have been the best presentation, but effectively, if there are no negative eigenvalues, you'll always get that this state is separable. You'll always get that the metric gives 0, effectively because the counting is 2 times the sum plus 1, so the 1's always there. So the important thing to note is that it can always, if your state is separable, the negativity will always be 0. The converse is not always true. If your negativity is 0, it doesn't always mean that your state is exactly separable. There's a slight subtlety in that there are some entangled states which have negativity 0, but they're kind of unique in this quantum information language because you can't extract any entanglement. You can't use it for any operations. They're called positive partial transpose. So if you act with local unitaries, you can't say extract a Bell pair and use it for anything. Anyway, there's a slight subtlety with the fermionic case, but basically this is really, really good at telling you if your state is very likely to be separable, or in this very unique case of oddly entangled states. So to give an example of this, a slightly more fun one, I'm going to look at, again, 2 different systems. We're going to look at the 1D Kitaev model, or Kitaev spin chain, and then we're going to look at the SSH model. So to distinguish the phases, I'm just going to set the pairing to the hopping so that they're equal, and you should be able to distinguish the different phases when mu over t is less than 2. And then for the SSH, obviously it's going to be different sides of whether the ratio of the hoppings is one is bigger than the other. So again, if we split this up in this kind of fun tripartite way, what you have is you're effectively looking at the coupling between the 2 different regions inside your linked density matrix. And the negativity is actually going to be sensitive to the coupling specifically on that links these 2 regions. And because of that, it can capture exactly what phase you're on based on the type of link that exists on that boundary. So for the Kitaev chain, what you would expect is a Majorana link in the topological phase, and that's kind of what you get. And you can tell because in the SSH phase, you would expect, you have a linkage of 2 fermionic degrees of freedom, or like you have a normal fermionic link, and you get that, yeah, there's a coupling of 2 states. One's coupled to the other across this boundary. But in the Kitaev case, it's a Majorana chain. And so you expect that there should be half the degrees of freedom on that kind of bond. And that's exactly what you see. The amount of information shared across that bond goes to, well, half that of the SSH chain. Also, if you go to the other phase, there's no coupling, and so the negativity will eventually die to 0. So this is really, really cool. This decomposition also allows you to do some very, very fun things, because if you take the rest of the system to be very large, you can treat it as an entropy bath, entanglement bath, in a kind of similar way that you normally think of in thermodynamic systems, a heat bath to keep systems at the right temperature. So you really isolating to just the behavior that interacts between the two of them. So that's all I have for right now. Some takeaways. Quantifying multipartite entanglement is really hard and can often be frustrating, either computationally or trying to have a conceptual handle on it. Different measures are suited to different tasks. Some of them are much better at understanding what you're performing. Some of them are good at capturing topological information. Some of them, like the negativity before, are good at handling, say, mixed states and honing in on separability. You can get a lot of information by looking at the scaling of entanglement entropy, or by using different measures on different subsystems, whether they be a bipartite or tripartite distinction. And they can be very useful at revealing quantum phase transitions or topological order. So some resources to look at or that I use for this talk. Harlow's lectures on quantum information, quantum gravity, a review here. Xiaogang's book is really great, though it's kind of all over the place, just in case. And the last introduction, I only suggest to the brave of heart or those who really want to go into quantum information. That's it.
Cool. Thank you, Makinde.
Sure. So any questions? Ethan, I open the floor for you to grill me again.
Well, yeah, I mean, I have questions, but I don't know, maybe anyone else wants to.
I also have some questions about the log L scaling.
Yeah.
So first of all, what happens, like if I'm thinking about, you know, this is my dispersion and I set my chemical potential to only fill up, let's say, one single mode. What does the entanglement scaling look like then? So if it's not like some superposition, it's just one single mode. Does it?
So you're saying that there's one mode across the entire chain.
I guess what my thinking is just like, if so a Fermi surface has a characteristic length, which is 1 over kf.
Right.
And if 1 over kf is smaller than L, then maybe it scales like log L. And if 1 over kf, in this case, kf is extremely small because it only encompasses one mode. So 1 over kf would be like the whole system. So it's much bigger than this small subsystem L. And then maybe it doesn't scale like log L. I don't know if that's true. That
I'm not sure. My intuition would be that it would still be. I feel like it still would be. Again, because you're not counting. Well, the number of states you're going to interact with is going to be like basically proportional to like the overlap of this with stuff, say, outside your system. So if you have like one K state, think about this, then you have something which is going to look like effectively something that's almost uniform across your spin chain. So now if you take all of your
so would it scale like L then?
Yeah,
would it be volume law?
Isn't the like reduced density matrix in real space just a proportional to the identity, right? If the mode is at zero momentum.
Yeah.
So then like the log L is coming from some like cancellation between the modes of different wave vectors or something as you add them up. Because when you fill the whole, when you fill all of the Brilliant zone or something, you have electrons at all wave vectors, right? You're supposed to get zero, I guess, right?
Right.
It's totally jammed. So yeah, maybe there's some.
Yeah, no. So yeah, you are right. Basically, you can think about this as the case where only one mode is active. Uh, in this case right here is basically saying that you're right about to transition out of the phase where logarithmic scaling is actually valid. So if you look at, say, the XY model that we were actually doing, we transformed that into a fermionic state where you had various excitations. So when you have one, it's saying you're transitioning from regime, I don't know which one did I put it, 3, where you have a few active, to 1 or 2, regime 1. And that's basically saying that you're going from a phase where you're all aligned with a magnetic field to where you have like one slight excitation away. The XY regime, that's saying you have like one phase oscillation or something. So there's some correlation that's still going to be there, and it's likely going to be transitioning out of that logarithmic phase, but it probably, my guess is that it won't just be the regular, I don't know, it's going to look weird. I don't think it's going to be just a standard constant.
Okay. And I get, maybe this is an obvious question, but you also said it at some point that because the correlation matrix was diagonalizable, the density matrix was simultaneously diagonalizable. Is it obvious that they commute?
No,
Okay.
that's a really nice coincidence of this, basically this being a free fermionic system. So if you want to find the same transformation that you do to make the correlation matrix diagonal in this reduced system, is going to be, well, it's just a transformation of a bunch of unitaries of, or a bunch of creation and annihilation operators. And so they're just creation and annihilation operators at one specific site. So in a free fermionic chain, that should only really, those will only produce something if they line up on the same site. Basically, it should be diagonal on the number basis. Both of them should be. And so, yeah, I don't know. It's a really nice coincidence that makes this thing solvable, but for like almost any other interacting model, it's just not there.
Okay. Yeah, because I was like, that seems super useful. I wonder why I didn't hear more talks when people talk about like entanglement spreading or whatever, talking about correlation, like some sort of mapping like this.
It's like effectively what you want is actually, you want to understand the correlations that you get from entanglement entropy, but this direct connection is like, it's a miracle. It's why this example is one of the first ones everyone pulls out, because you can just immediately do it.
Cool.
I have like two quick questions. One quick question is, I was just curious, are there, do people know of examples where this analytic continuation for the Rényi entropies doesn't work?
Yes, there are a couple. I'm forgetting off the top of my head. There are some really annoying ones for, particularly for some class of mixed states. I'm forgetting exactly what they were, but there are a few cases where you actually need to be careful before taking this limit.
Okay.
Yeah,
so
most people do it without thinking about it, though.
Yeah. Right. Yeah. So I'm just wondering to what extent most people are getting wrong answers. I guess there's yeah, I don't know.
So the nice thing is it's if I remember correctly, it's effectively only for this class of like specific mixed states. And most people who are doing entanglement entropy, because they care about the entanglement entropy at the end, they almost explicitly using pure states, and they're just using Rényi entropy because it's easier to calculate. So in those cases, it's totally fine, and they're not getting anything wrong. Some of the issues come up if in the like new measures that people are looking at, where they apply it to mixed states and then they want to take this limit, and every once in a while there's some weird subtlety that they get called out for.
Yeah, I see. Okay, and then I also was curious. I don't know if this is answerable, but if you you were saying that generic high energy states, whatever, you look at entanglement entropy, and these guys, you generically expect some kind of volume law scaling, right? Whereas ground states, say gapped ground states, are area law. So do you like what happens if I consider like a system at a very small, like, but non-zero entropy energy density? Like I turn on some small temperature, right? Like, and I look at the entanglement entropy. Do I immediately get some like small volume law term in the entanglement entropy, or is the scaling like dependent on? Does it like cross over from area to volume at some length scale set by some like thermal length or something?
Yeah, there. I'm not going to say this with 100% confidence because it's kind of subtle, and I mostly punted away from entanglement entropy itself as a metric because of this issue. But you can see yeah, basically what I'll say is I'm not 100% sure. I expect that there would be some kind of like some weird crossover, like temperature length scale at which things would actually would emerge. You can see with lots of these other metrics which are capable of dealing with mixed states, that there are specific transitions where like these corrections, whether they be logarithmic corrections or subleading terms that emerge, vanish or like change at particular temperatures. So there's like a temperature length scale at which they vanish or they transition themselves. I expect that would be the case with regular entanglement entropy at a particular temperature scale, but I'm not confident enough to say.
Yes, so you have to wait until the thermal length gets of order of the system size before you talk about being in the area law or the volume law.
Volume. That's my intuition.
Okay, cool. Makes sense.
Yeah.
That's interesting.
Yeah. Anyone else? I apologize. This is super cobbled together because most people talk about things in for their own field, and not many really consolidate towards even this type of interest for condensed matter. So this wasn't really taken from a single source, and I kind of threw it together this week. So if it was confusing, I apologize. Hopefully it was intuitive.
Very fun and enjoyable. Sorry. Do people ever do entanglement cuts in like momentum space or something? Like, why are we always living in real space when that might not be the best
very
system?
good question.
No, it's actually a really good question. The reason we typically do it is because we like to think about local operators. So we like to think about observables in some kind of restricted, in some kind of restricted position space.
Well, I don't know. I mean, when I feel like maybe let's say half of condensed matter physics in experiments is done in the frequency momentum domain. right?
Well, it's not the like basis in which we do things. It's the like the observables that we tend to speak about. So if you're thinking about, say, I'm looking at some current density or something, right? Even when you measure the current density, usually you're going to be seeing it as some kind of, it's going to be like correlated to, I don't know, some kind of transition or light or something.
But I mean,
Like
normally my light source is going to be some plane wave at some frequency, right? And I'm measuring like a response coming from the whole sample or something, right?
Yeah.
That's also true of like neutron scattering or any.
Yeah, sure. I mean, it just depends on whether the experiments are using particles or waves, right?
Right.
I'm just claiming that in very many cases you're usually using like wave sources as opposed to particle sources or something. Well, in any case, it's just a matter of perspective, right? And so, you know, deciding whether you want to do real or momentum space cuts. Well, I don't know. Yeah, I wonder if there's any kind of motivation.
So I think my normal intuition would be to say that the operators that we use for observation are typically local in some source, but I think the more fundamental answer is probably that we expect the fundamental Hamiltonians governing the system to actually have some kind of local interactions. And so if you want to look at
but the local interactions might be at some like crazy energy scale that is not relevant to like you know, we have a metal or something, right?
Right.
The low energy stuff is happening in momentum space, not in.
Right. So I think you're right. The reason I think it's probably held up, at least for this kind of this like decomposition scheme, is because I think typically talk about like we're looking at specifically like ground states of systems. So have some kind of arbitrary Hamiltonian, which is going to have connections between things. And again, I think this is likely more of an intuitive thing than a strictly necessary thing. But if you have a Hamiltonian built up of a bunch of local connections, probably want to be sensitive to like interactions or couplings between local subsets or subsystems. And then if that's not the case, if you have some kind of long range coupling, that should be something kind of unique or special. So you want to be sensitive to it, but say in like, if you have a bunch of really tightly coupled things locally, but some arbitrary systems really far away aren't coupled that well, I expect that, you know, if you transition to looking for couplings in momentum space, that the distinction between a bunch of different phases is going to become a lot less sharp. That's again just my.
But I guess maybe what I guess what I'm trying to say is that we're in condensed matter physics, at least we never care about the like correlation function. Well, we never care about like what the actual microscopic UV Hilbert space is, right? We're just interested in what's going on at low energies and at large scales and stuff, blah blah blah. So having some like real space measure that's like sensitive to, that is like doing, or maybe that's fine as long as you remove the like UV contributions to the entanglement entropy or something.
Yeah, I mean, I guess, so I could imagine, like, let's say I have a 2D lattice, and I put spins up in some region and spins down in some other region. And like, let's say I draw a circle, it's all spins down here, it spins up here. That's exactly the analog of like filled or unfilled for a 2D Fermi surface. It's just in real space versus K space.
Mm-hmm.
So if I think about defining the entanglement measure in K space, and I look at a small region of K space, it's going to scale like log, since even though my real space is
but in K space, isn't it just a product?
Well, it's a product in real space.
In K space, it's just a product.
if it's a Fermi surface, but what I'm proposing is flipping the K and real space pictures. So like, let's say that I have a really strong magnetic field in one region and other region it's pointing the other way. So all my spins are like this in a circle in real space, and then the other way in real space. So in K space, it will look as if it's the real space picture from a Fermi surface. So if we define entanglement measures in K space, it will scale like log of the region in K space. And instead of that telling you there's a Fermi surface, it would tell you that there is a distinct region in real space, like where all the spins are down versus all being up. Like, I guess what I'm saying is the scaling there is telling you different things, but they are maybe useful. Like if you imagine having puddles of down spins versus puddles of up spins, the scaling in K space might tell you about that.
That's actually really interesting. I wonder if the constraint is actually that you expect some kind of conserved particle number or something, because in this, like the different scaling, like it's since the cut that you put on is basically going to be like a filling in this flipped I don't know, this flipped way that you just defined. So to see the different scalings, you would have to put in different filling numbers to this system.
Yeah.
So I was under the impression that most of this is applied to like few body systems in AMO, like NV centers, like, I don't know, optical systems, and not or optical or things that are on optical lattices, but not really materials where the UV scale is far from the scale that you're probing. So I thought, like, motivated by that was that people use real space in these things.
Yeah, it could be. My question could just be coming from the fact that I care about condensed matter. I'm like I want everything to apply to condensed matter physics, right?
So I think that's why the bulk of the work is done like in real space. That maybe and people have not thought like how these translate for gapless systems like too much, or I don't know how the field goes in that direction.
There has been work done on gapless systems, but they're much more complicated. There's less of an intuitive picture, again, because if you don't have this like nice exponential fall off of correlations, you don't expect a normal area law, and you have to be very careful about the counting. But there are things that have been done, but you're right, they tend to still be done in real space, and I'm not sure that's necessary. Yeah, that's a cool point.
All right. Thank you, Mockingjay. This was very good. Next week, we will have Changnan, who is talking about some undergrad work he did at Caltech on Anderson localization. So that should be interesting.
Cool.
Hey. All right. Thank you, everyone, for attending, and I will hope to see you next week.